All right, so we're beginning Unit 4 with the sources of magnetic fields. Thus far, we have only spoken about what, we just took as a given. Here's a magnetic field. What happens to things in that magnetic field? So if a charged particle is in the magnetic field, what does it experience? Well, that depends. If it's not moving, it experiences nothing. If it has some velocity, if it's moving within that magnetic field, and if a component of its velocity is perpendicular to that magnetic field, then it will experience a magnetic force. But we haven't yet spoken about where does the magnetic field come from? What creates the magnetic field? Well, it turns out that moving charge creates the magnetic field. Just like you need a moving charge to experience a magnetic force, you need a moving charge to actually create the field to begin with that then creates the magnetic force in another moving charge. So two people are credited with working this out, Biot and Savart, and they came up with a mathematical expression that gives the magnetic field at some point in space due to a current. So the magnetic field at some point here, we say this is point P. This infinitesimal tiny piece of magnetic field, dB, at point P results from this current, I, moving along some infinitesimal piece of a wire, ds. And we're assuming, of course, right now that the current is steady. It's not a variable current. That is another complexity that we won't go into. So let's unpack this well, let me bring up, let me say this is an empirical result. This is not derived from some higher order law. This was something we noticed, Biot and Savart noticed experimentally, and they worked out a mathematical expression to describe that. They also noticed that the magnitude of this tiny piece of the field dB is proportional to sine of theta, where theta is the angles between vectors ds and r hat. Looks like I left r hat off of this slide. I'll fix that. So the result is Biot-Savart's law. The infinitesimal piece of the magnetic field, which is a vector, remember, is equal to some constants multiplied by the current, the cross product ds cross r hat, divided by the square of the distance between ds and this observation point P. So what are these constants? This is the permeability of free space, mu naught, the Greek letter mu. So this kind of gives you the strength of the field, the way in which the field can permeate through some material. And mu naught is the strength, the ability of the magnetic field to get through vacuum. If we were underwater or in some other medium, we would not use mu naught because we're not in free space anymore. This is the current I. Now ds, of course, is this infinitesimal piece of wire or piece of conductor or whatever the current's flowing through, and this vector has the direction of the current at that instant. Now what is r hat? Well, that is the unit vector that gives the direction of r squared. So in other words, we could say that, let's see if this works. Let's do purple, that's a little different. So we could say vector r, which connects ds to the observation point, has a magnitude of r and a direction of r hat. So the unit vectors have a magnitude of 1, they just give direction. So r hat points in this direction. The total vector r would be the vector that connects, oh boy, that's a wavy line, would be the vector that connects these two things. I'm making it worse. So that vector r would connect this point to that point in the direction of r hat. So what's the direction of the magnetic field, at least for this point here? Use your right hand rule, if you remember. Point your first finger in the direction of ds, your second finger in the direction of r hat, and your thumb points in the direction of the magnetic field. Let's see if I can do this a little better. So since we have some current, we've got ds in this direction. Point P is over here. So r would be the vector that connects these two, but the direction of r is r hat. So if Savart's law says that we have to take the cross product of ds, which points in this direction at this moment, and our second finger points in the direction of r hat, which is just the direction of observation, our thumb points in the direction of the magnetic field. So over here, the magnetic field points out of the page. If I were to look at a point on the other side, let's say it's P2, whatever. So now R2 hat points in this. This is going to be really hard for me to do on this camera. I'm going to stand up. Well, actually, no, I've got to twist my arm the other way. So my first finger points in the direction of ds. My second finger points to the observation point, which is now underneath the wire, and my thumb points in the direction of the magnetic field. So on this side of the wire, B2 at this point is into the plane of the page. What if we were like above the wire, like in the air over here? Well, ds, and now this is hard. Now my middle finger is going to point straight up in the air. And the magnetic field for that point will be across the wire. So what you see is happening here is the magnetic field is coming out, it's coming over, and it's going down, and on the other side, it's going to go back again. It's making a circle around this wire. Get my mouse. Okay. And r squared is just the distance from the observation point to the piece of wire ds squared. So to find the total field, you sum up all the contributions from the current elements. You take the integral. So this is a brute force technique, and what I mean by this is like Coulomb's law, where you can apply it theoretically to any situation. It doesn't matter, it will always work. The problem is sometimes the math will be really difficult to do. Sometimes this integral will be very nasty. And so we'll have a way of dealing with highly symmetric situations later, just like we had Gauss's law for highly symmetric situations involving electric charge. We'll have Ampere's law for highly symmetric matters of magnetic fields and so on. So a few notes about this stuff. The magnitude of the magnetic field varies as the inverse square the distance from the ds element. The electric field due to a point charge also varies as an inverse square of the distance from the charge. The electric field created by a point charge is radial in direction. The magnetic field created by a current element is perpendicular to both the length element and the unit vector, so a little bit different there. The current element producing a magnetic field is part of an extended current distribution. So some similarities, but a lot of differences between the two things. So let us look at a problem. So this problem asks us to apply Savart's law here to a simple situation of a current carrying wire in order to find the magnetic field at some point distance a away, and we call that point P. So we first start with Savart's law, and we're going to break down this expression little by little so we can fit everything in terms of one variable that we can integrate. And that variable that we're going to integrate along is the angle theta. Now you could use this angle here, but it just seems more intuitive to use this angle theta, and we're going to integrate from one side through 180 degrees all the way to the other side. So the most complicated part of this is the ds cross r. So why don't I look at that real quick first. ds cross r. Well, this is a cross product between two vectors that results in another vector. So the result of this is going to have some magnitude and some direction, which will be given by a unit vector. So we need these two pieces of the puzzle. Well, probably the simplest thing, or I guess the quickest thing, is to first talk about the actual direction. So we need the vector ds, and we need the, oh, I'm sorry, this should be r hat, not r. That's a mistake I made. So where is ds on here? Well, this ds is this infinitesimal piece of the wire along which the current is flowing that has some direction in the direction of the current. So this is ds right along the wire. Now what about r hat? Well, the vector r points from this infinitesimal element to the observation point P, and r hat is just simply the direction of r. Using the right-handed rule for cross products, you point your fingers in the direction of the first vector, which is ds. You curl them in the direction of the second vector, which is r hat, which points to P, and your thumb points in the direction of the cross product. Alternatively, you could use your index finger in the direction of ds and your middle finger in the direction of the second vector, r hat, and your thumb points in the direction of the cross product. Now, the problem with this method is that sometimes people reverse the two vectors. Your index finger always points in the direction of the first vector, middle finger points in the direction of the second vector, thumb is the product. You can eliminate that mistake by using this other method of saying point all your fingers in the direction of the first vector and move them, curl them in the direction of the second vector, and then their thumb points in the direction of the product. So since we know that the magnetic field is going to have the direction out of the page, and that comes from the cross product here, we can say that that has the direction of k hat, positive k hat. Okay, so now what is the magnitude of the cross product? Well, we know that can be found from the magnitude of ds times the magnitude of r hat, and that gives us the magnitude of the sine of the angle between them. Call that phi dsr. So the cross product ds cross r hat is equal to just ds. The magnitude of r hat is 1. Notice I dropped the vector bar to indicate the magnitude here. And this angle, phi dsr, that is this angle here, phi dsr. Can I put that in terms of theta? I mean, yeah, you can. You can say that is 90 degrees minus theta, which phi dsr equals 90 degrees minus theta, because this is a right triangle. So if this angle is theta, this is 90 minus theta. There you go. So the reason I did that again is I wanted everything in terms of this angle, and that's what I eventually went to integrate over. But is there a more elegant way of putting this? Yeah. Sine of 90 minus theta is cosine of theta. That's just a property of geometry. Oh, and I forgot my k hats here. This vector, I can leave off the 1 now. The magnitude is 1. ds, since this is along the horizontal, let's just call that dx. So say ds equals dx. So ds cross r hat equals dx cosine of theta k hat. So far so good, right? Except that the x is going to be changing in this problem. as you're moving along this wire. So now I've got two variables that are changing, but the two relate to each other. Dx depends on theta, so how could I relate the two? Try to combine them so that they're both a function of theta instead of having two variables here. Well, I can relate x to some other stuff. So let's say I want to sine of theta, for example, is opposite x over the hypotenuse r, right? But now we've got r into the picture here, and that doesn't help us a whole lot because now r is going to be another variable. If I solve for x and put it in terms of r, well, then I've got to somehow relate r to theta. So that's not where I want to go. If I look at cosine, I get a over r. Well, that doesn't help me with x. So what if I look at tangent of theta? Well, that is opposite x over adjacent a. And I'm just talking about the whole distance here of this triangle x over this whole distance a. So then x equals a tangent of theta. Now, the way your book does it is they say that x is negative a tangent of theta because we're on the negative side of the origin, or the origin is right here under P. There are different ways to do this, but I'm just going to go with what the book says and say this is negative. Now this will get, I think, a little bit more confusing when we talk about the limits of integration, but so be it. So now I've got x, but I need dx. So I can differentiate dx with respect to theta. We've only got one variable, so I can do that. And end up with negative a secant squared theta. How did I get that? Well, you just know that the derivative of tangent is secant squared. If you don't know, you look it up in a table. If you want to know why, ask a mathematician. I believe this is something we learned in calculus class. So, yeah, you can look it up in the table for this class though. So then dx is equal to negative a secant squared theta d theta. So let me go back to this expression and say ds cross r hat equals negative a secant squared theta cosine theta d theta r hat. I just moved the d theta to the outside. Okay. So I think we're pretty good on this part of Savart's law. We have everything in terms of theta. We can integrate. Now we've got that r we've got to deal with, because remember r is a variable. It's changing as you integrate along this wire. So we need to express that in terms of theta as well. So I can say r, the hypotenuse, just magnitude, no direction, is equal to x squared plus a squared. But now I'm back into the x business again. So I would have to do some more to deal with that. So let's not go there. We can say, though, that r is equal to a over cosine of theta. Remember, because cosine of theta equals adjacent over hypotenuse. So I can write it like that. If I wanted to, I know Savart involves a 1 over r squared term, so I could say 1 over r squared is equal to cosine squared of theta over a squared. So going back to Savart's law, dB is equal to, bring these two things down, your constants out here, mu naught over 4 pi times I, can't forget the current. Now I've got this cross product that is here, and it is negative a secant squared theta cosine theta d theta k hat times 1 over r squared, because you're basically multiplying this by 1 over r squared. So this is times cosine squared theta over a squared. So now we just need to simplify things. Now, maybe you remember that secant of theta is 1 over cosine of theta, so that helps things quite a bit because I've got a cosine squared term and I've got a secant squared term. So these two cancel each other out because this is 1 over cosine squared and this is cosine squared. So those two go away. Also, I have the negative sign. You can move that out. And one of this a cancels, and this exponent is reduced by 1. So dB then is equal to negative mu naught I over 4 pi times cosine of theta d theta k hat. Now the next thing we need to do to find the total field is we integrate. So I'm going to leave all the constants to the outside. Negative mu naught I over 4 pi. And I know we get used to putting the unit vector on the end, but I'm going to move it out here, which is okay, just so I can keep all my integral stuff to the right-hand side. And we're going to integrate from theta 1 to theta 2. So what is the integral of cosine of theta? Well, that's actually a nice one. That's just sine of theta. For 4 pi, my negative, don't miss the negative, k hat times the integral of cosine of theta, which is just sine of theta, integrated from theta 1 to theta 2. So this is where I think it gets the trickiest part. What is theta 1 and theta 2? Well, we start, if we're integrating over an infinitely long wire, then this theta is going to approach 90 degrees, right? So we're going to start at a 90 degree angle and end up at a negative 90 degree angle on the other side. So we start out at a 90 degree angle here, and we end up with a negative 90 degree angle here. Now, it may seem more intuitive to you, and honestly, myself included, if we're moving in a counterclockwise fashion to say, let's start off at a negative pi over 2 or negative 90 degree angle and end up at a positive 90 degree angle. But that's not going to work well over here because we have to start with x being negative. And if you start with a tangent of, if we look at, say, some tangent of whatever, tangent of positive 10, you get a positive number, and so we have to have the negative here to make it negative. If you look at tangent of negative 10, negative whatever, you get a negative number, so this negative could not be there because the x has to be negative from the beginning and end up positive. So somewhere there's got to be a negative there. If you insert the negative here, then you must integrate from positive pi over 2 to negative pi over 2. These things have to be consistent. So I can say this is from pi over 2 to negative pi over 2. Now I could take that negative sign and absorb it into the integral, into these integration limits by flipping them. I think that keeps things a little neater, but people often get angry when I do that, so I won't do that here. So mu naught I over 4 pi k hat times sine of negative pi over 2 minus sine of positive pi over 2. So negative pi over 2, what is that? That's negative 1 minus positive 1. So that's -2, right? And if you have a if you have a negative here, a negative there, they cancel. So B equals positive mu naught I over 2 pi. Where'd the 4 go? Well, because I've got a 2 from here, so that cuts that down. K hat. And of course, this should come out positive. It has to be positive because the direction given by the first right-hand rule of this cross product says that the magnetic field is going to point your fingers in the direction of ds, curl them in the direction of r hat, and the field must point up out of the page, positive k hat direction. So we should have gotten a positive answer. Now, if we talk about the second right-hand rule, the thing to come, a slide later in the presentation, the second right-hand rule says point your thumb in the direction of any current, and your fingers will curl in the direction of the magnetic field around that current. So my fingers are curling up and out of the page on that other side. If I were to look at a point down here, it would be the exact opposite. It would be pointing down into the page. Okay, so for a long, straight conductor, well, the magnetic field lines are actually circles, concentric with the wire. So they're circling around this conductor. The field lines lie in planes perpendicular to the wire. The magnitude of the field is constant on any circle of radius a. So at some fixed distance away from the conductor, the magnetic field is going to be uniform. And we introduced this right-handed rule number 2. So if you remember, right-hand rule number 1 is the one we introduced with the Lorentz force law, but it applies to any cross product. So you point your index finger in the direction of the first vector, you point your middle finger in the direction of the second vector, and your thumb points in the direction of the cross product, or between those two vectors. So for the Lorentz force law, that was QV cross B, or in other terms, IL cross B in the case of a wire carrying current. So L, B, and the force is in the direction of your thumb. The second right-hand rule is just kind of an extension of that, which we saw from the previous problem. The second right-hand rule says if you've got a current-carrying conductor, point your thumb in the direction of the current, and your fingers will curl in the direction of the magnetic field lines. So for this wire that you see in the picture, the current is pointing upwards, so the magnetic field lines curl in that direction. If you're looking down upon the wire with the current coming towards you, you would see a counterclockwise magnetic field circling around the wire. If you're looking underneath the wire with the current flowing away from you, you would see a clockwise, a magnetic field line that winds in a clockwise fashion around the wire. So looking at this example, in this problem, you have two wires carrying two different currents, and they're both coming out of the plane of the page. They're separated by some distance d, and we're asked the two parts of this problem. First, we're asked to find the total magnetic field at point P1, which is halfway between the two wires, and then we are asked to find the magnetic field at point P2, which is a distance d above the wire on the right. Call that carrying current I2. So we know the currents through each of these wires. We know the distance. We just need to find the magnetic field at these 2 points. So let's look at A first. Find the field at magnetic field at point P1. Okay, so we'll use the second right-hand rule to find the direction, and then we have that equation that we derived from Savart's law for the magnetic field some distance away from a current carrying wire. First, let me draw this in a little greater detail. So we have this wire, and we have the second wire, and they're both coming out of the page. the currents are coming out of the page towards you. So this is I1, this is I2. So what is the direction of the field surrounding this wire on the left? Well, we know the field is going to circle around that wire. Which direction? Well, we only have two options. And since we're using a right-hand convention and the current is coming out of the page at you and your fingers are curling around in the direction of the field must be going around in this direction. So B1 travels in that direction. Well, the other wire has the same situation. The current's coming up out of the paper, so the field's curling around counterclockwise. So we can say B2 looks like that. So how are we going to find... So how do we construct the field, the total field at the center? Well, the total field is just the sum of B1 plus B2, where these are vectors. So I'm adding the vector bar here. So we have to think about the direction of the two. Well, this field is circulating counterclockwise as we step out this direction. It will still be circulating counterclockwise, and likewise on the other side, still going counterclockwise, but the difference is because of where you are in relation to the wires, the field from the first wire will be pointing straight up, and the field from the second wire will be pointing straight down at that position. So remember, the current's coming out of the page, the field circles in the direction with which you curl your fingers. So since you're curling your fingers this way, on this side of the wire, the field points straight up. On the other, for the other wire, the field points straight down. Now, if these two wires were carrying equal currents, these two fields would subtract out, and the total field at that point would be 0. But they are not carrying equal currents. So we have to look at the magnitude of each one. Well, if you remember, the magnitude of the magnetic field some distance away from a current carrying wire is mu naught I over 2 pi r, where r is the distance away from that wire. So we can construct an expression for B1. We say that's just mu naught I1 over 2 pi. Now what is r? R is the distance from the wire to the point of observation. The distance between the two wires is d, so r must be d over 2. And what is the direction? We'll say that's, given the convention, the right is positive I hat, up is positive j hat. So we can say that is in the positive j hat direction. Now, we note that I'm multiplying d over 2 times 2, so B1, let's just simplify this a little bit, is mu naught I1 over pi d j hat. Likewise, we can say that B2 is just mu naught I2 over pi d, because we're the same distance away from the wire 1 as we are wire 2. But this one's going to be in the negative j hat direction. So when we are asked to find the total field at point P1, that's just B1 plus B2. So the total field at point P1 is mu naught I1 over pi d j hat minus mu naught I2 over pi d j hat. Lost a vector bar there. So I can factor out all the common terms and I get mu naught over pi d times I1 minus I2 j hat. which one has the larger current. That's I2. So this is going to end up being in the negative direction. If I put in the numbers for this, permeability of free space is 4 pi times 10 to the negative 7. I'm leaving the units out right now because I'm being a little lazy. Pi times 0.20 meters. I1's 3.0 amps minus 5.0 amps. Okay. And when you plug in the numbers, that is 4.00 times 10 to the negative 6 Tesla, and that is in the negative. Remember, the negative came from the subtraction, J hat direction. The next part of the problem wants us to find the magnetic field at some distance d above the wire on the right hand side. So let me sketch this again in a little more detail down here. I've got a wire here, wire here. Let me make it a little larger. This is point P2. So if I look at the magnetic field from this first wire, remember that it's going to circle around the wire in a counterclockwise manner. So the magnetic field lines are going to look something like this. That means the magnetic field at this point right here is in this direction. The magnetic field from this wire directly beneath P2, again circling around, the lines would circle around in a counterclockwise fashion. Like this. So at point P2, the magnetic field points horizontally to the left. So we're going to need to break B1 down into X and Y components and add that to B2. So what is the magnitude of B2? Well, that one's simple because that's going to be in the negative I hat direction, the negative X direction, and it's going to have magnitude mu naught I2 over 2 pi times the distance away, which is d in the I hat direction. That one's simple. B1, a little bit more complicated. So then, we have this triangle. In this case, it's an equilateral triangle formed by these two wires because they're distance d apart, and P2 is distance d above, so that's an equilateral triangle. This angle equals that angle. This is the right angle, and you're looking for B1, which is at some angle above. Well, if we look at free body diagram, B1 makes some angle with the horizontal. What is that angle? Well, let's do some trigonometry here. If we extend the line of the triangle upwards, we'll know that this is also theta, which means this is theta. This is a 90-degree angle, so this angle would be 90 minus theta, but since it's an equilateral triangle, 90 minus theta just equals theta. The two angles are equal. So that means this is angle theta. Okay, I'm going to break this down into x and y components. This is vector B1. So this is B1x, B1y, and the total vector B1 is of course B1x I hat plus B1y j hat. and that will be negative b1 cosine of theta I hat, because it's in the negative direction, and we get the magnitude by looking at the projection onto the x-axis by using cosine. And in the y direction, that's positive b1 sine of theta j hat. Well, what is, we haven't found theta yet, so we can't take cosine of it, but we can, we don't even have to find theta. We can just find cosine of theta outright, because cosine of theta is adjacent over hypotenuse. The hypotenuse is d squared plus d squared, which is just root 2d. So cosine of theta is adjacent d over the hypotenuse, root 2d, or just square root of 2 over 2, because it's a 45-degree angle. And we know that sine of theta will give us the same result. Okay, so b1, I can factor out just this magnitude b1, and that leaves me with negative cosine of theta, which is root 2 over 2 I hat, plus sine of theta, which is root 2 over 2 j hat. Well, I can factor that even more and say this is b1 times root 2 over 2 negative I hat plus j hat. So then the magnitude of b1 is mu naught I1 over 2 pi times the distance away, which is root 2d. And then, of course, we have to include our square root of 2 over 2 and negative I hat plus j hat. Okay, I can simplify this quite a bit, I think. Okay, the square root of 2 cancels out. You end up with 4, so that's b1 equals mu naught I1 over 4 pi. To do that, d negative I hat plus j hat. So we need to add b1 and b2 to get the total magnetic field at p1. So it's b1 plus b2, or mu naught I1 4 pi d negative I hat plus j hat. That's b1 plus b2, which, where did we write that? All the way up here. So it's going to be a minus mu naught I2 over 2 pi d I hat. So now I can factor stuff up, make this stuff a little nicer. See, common to every term is mu naught over 2 pi d. For the I hats, it would be, let's see, negative I1, whoops, I1 over 2. So I1 over 2 gives me, yep, that's right, and minus just I2, I hat, plus 1 over 2 j hat. Oops, I'm sorry, I got out of the recording window. And I missed an I1 here. That's 1/2 times I1. Okay, so now it's just a matter of plugging in the numbers. 4 pi times 10 to the negative 7th Tesla meters per amps over 2 pi times d, which is 0.20 meters, minus I1, which is 3.00 amps, over 2 minus I2, 5.00 amps, I hat, plus I1, which is 3.00 amps, over 2 J hat. Okay, so you've got 1 times 10 to the negative 6 Tesla per amp times these two components. So that gives you negative 6.5. So this math is easy. 6.5 times 10 to the negative 6 Teslas, or micro Teslas, I hat, plus 1.5 micro Tesla. Again, same thing there. J hat. In this problem, we've got a current that flows down some wire towards some point P, then stops, forms a circular arc, and then flows outward away from P. And we want to know what is the magnetic field at this point P. Well, first of all, this is kind of a convoluted setup. Why do we care about this? This is actually a very important problem, a generalizing problem, because as we'll see at the end, we'll use this setup to extend to a full circular loop, which is something that comes up all the time, and we'll be able to calculate what the magnetic field inside that circular loop is. Okay, so first we start where we always do, with Savart's law, U naught over 4 pi times I ds cross r hat over r squared. And we also note that we have really 3 distinct sections here. We have section 1, section 2, and section 3. Because different things are going on in the different sections. So let's just look at them individually and add them up. And note that, let's look at section 1 first. So, dB is going to have some magnitude and direction. So let's look at the direction first. We've got current flowing down this way, and r hat, which is in the same direction, r hat points towards point P, which is in the same direction as the current. So since those two things are pointing in the same direction, the area of that parallelogram that mapped out by the two vectors, which would be my two fingers here, that area is 0 because they're in the same direction. So this whole thing is 0. Let's look at it another way. ds cross r equals the magnitude of ds times the magnitude magnitude of r hat, which we know is just 1, times sine of the angle phi dsr. Well, this angle is 0 because I hat points in this direction, and I points in this direction. ds here points in that direction. That's the wire that we're integrating along. And r hat points in this direction because the vector r connects ds to the observation point, and r hat is the direction of that. They're both in the same direction. Sine of 0 degrees is 0. So dB1, I'll call it, equals 0. Well, what happens here? Section 3. Well, this is this has some magnitude and direction like before. And let's look at the direction by looking at this cross product, that part of Savart's law. So ds cross r hat equals magnitude ds times the magnitude of r hat times sine of the angle between ds and r hat. Let's call that dsr. Well, point your index finger in the direction of the first vector, your second finger in the direction of the second vector. Well, now we've got a 180-degree difference between these two. The area of that parallelogram, again, is equal to 0. Sine of 180 degrees also equals 0. So this cross product equals 0. So the magnetic field all along section 3 equals 0. So the magnetic field at point P from this section and that section is 0. Now that doesn't mean that there's no magnetic field from these sections. There's going to be a magnetic field here, for example. In fact, that's going to be out of the page, and here the magnetic field is going to be into the page from this section of wire. But the magnetic field contribution at point P from section 1 and section 3 is 0. So therefore, we only have to worry about this circular curved piece of wire. I'll zoom out just a little bit and get more of the page in. Okay, so section 2. So dB equals mu naught over 4 pi I ds cross r hat over r squared. Well, we know r squared is just going to be a because that radius is constant the whole way around. Let's deal with this cross product real quick. So ds, we could call it ds2 if you want, but you just know that the s is different for each one of these, as is the r. So ds cross r hat is equal to the magnitude of ds times the magnitude of r hat times sine of the angle between ds and r hat. I won't put the symbol in there. Well, what's the direction of ds? Well, that is tangential to the curve at all points. ds changes. It is in this direction at the very beginning, and as you move along the curve, the direction with which you're moving changes, so ds's direction changes. It's always tangential to the radius that points towards the center. It's tangential to the curve, a right angle to that radius vector. So phi dsr equals 90 degrees everywhere you go along this circular loop. So sine of 90 degrees is equal to 1. So ds, since this is a vector, I also need to add the direction here. So this is kind of hard to do where I'm sitting, but my index finger points in the direction of ds, let's say this spot right here. My second finger curls in the direction of the r hat vector, and my thumb points in the direction of the cross product. My thumb is pointing into the page if you couldn't see that. So that is in the negative k hat direction. So ds cross r hat equals the magnitude ds times the magnitude of r hat, which, remember, the magnitude of r hat is equal to 1. The r vector has some magnitude equal to a, where r vector equals the magnitude r times r hat to give the direction, and in this case is a times r hat. But here we're just worried about the magnitude of r hat, so let's just multiply by 1 times 1 again. Well, what is ds? Because we're going to have to integrate this along something, right? Everything is constant except the angle theta that is changing. So if we say this is 0, then down here we traverse some angle theta. So this is going to be at some angle d theta. Well, if you remember from circular motion, s equals r theta. Some arc length s is equal to the radius times the angle subtended by that arc length. So ds is just equal to r d theta, assuming r stays constant. Here, because r is equal to a, say ds equals a d theta. So this vector ds cross r hat is equal to a d theta times 1 times 1. So we'll take this, and times negative k hat. Forgot that again. So we'll take this whole vector and dump it into Savart's law. Right here. And we also have to say that r squared is equal to a squared, and put that in as well. So dB is equal to mu naught I over 4 pi, pull out all the constants, times negative a d theta k hat over a squared. I'm going to move things around a little bit, simplify it some. So that's negative, this cancels, mu naught I over 4 pi a d theta. Actually, let me put the k hat, like we did on another problem. I'll put the k hat in here, so then I just have all the stuff I'm integrating on the outside. How do I get the total field? Well, I have to integrate this. Integrate that. So the total field at point P is equal to negative mu naught I over 4 pi a times the integral of this. And if I evaluate it from 0 to theta, this becomes theta k hat. And that is a vector. Should have a vector bar on it. So for a complete loop, too many O's. For a complete loop, you want to integrate from 0 to 2 pi. So theta final equals 2 pi. Put that in the expression I've just found. B equals negative mu naught I over 4 pi a times 2 pi k hat. Well, the pi's cancel, the 2 cancels, that becomes 2. So B equals negative mu naught I over 2 a k hat. Now the direction depends on which way you choose to be the positive and negative and so on. So most of the time you'll see this just written as the magnitude of the magnetic field at the center of a loop is mu naught I over 2a, where a equals the radius of the loop. We discussed what the magnetic field from a current loop would be. It's going to look something like this. The magnetic field will be fairly straight and uniform within the loop, and curl on the fringes. It will curl and encircle the sides. So if you just think of a straight piece of wire carrying a current and bend it around over on itself, you would get a field pattern something like this. And if you were to, actually do this experiment with some iron filings and run some current through a loop of wire through that plane, you would see that field pattern mapped out. Let's look at an example real quick of a combination of the two situations we've been visiting. If you have a large straight wire carrying a current of 8 amps and a circular loop of wire that carries a current of 2 amps and has a radius of 0.03 meters, find the magnitude and direction of the magnetic field at the center of the loop. C3007. All right, so we've got a wire carrying a current I1 downward, and we've got a loop of wire carrying some current in a clockwise fashion, and we want to know what the magnetic field is right there in the center of the loop. So the total magnetic field is just going to be the magnetic field from the wire plus the magnetic field of the loop. So let's find individually what each one of these values are, and then we can add them together and get the total field. So the field from the wire, we use the equation. Let me write down the known values first, getting ahead of myself. So I1 is 8 amps, I2 is 2 amps, and the radius is 0.030 meters. Okay, so the magnetic field from any straight piece of wire is mu naught I, and in this case that's I1 over 2 pi A, where A is the distance from the wire. Here A is going to equal R, because you are a distance R away from that wire. And I didn't add direction. If, I may have to stand up to show this, if the current is traveling downward, I put my thumb in the direction of the current and curl my fingers in the direction of the magnetic field. So you can see my fingers were curling up out of the page. So I'll say this is in the positive k-hat direction. Out of page. So what about the magnetic field from the loop? So I call that V sub L. So this is a circular piece of current carrying wire. So that's mu naught I2 over 2 A, again, where A is the radius of the loop. These two expressions look really familiar, but make sure you don't confuse them because this has a pi and this does not have a pi. You would think the circular loop would be the one with the pi, but that's not the case. It's the wire that has the pi in the expression. And this is just an equation that'll be given to you. So, and the direction, we need to add the direction. If the current's going clockwise, point my thumb in the direction of the current, my fingers curl inward the whole time. So this would be in the negative k-hat direction. So that's mu naught I2 over 2 pi r negative k-hat into page. All right, so now we can just add these two expressions. The total magnetic field is this expression, mu naught I1 over 2 pi r k-hat minus mu naught I2 over, see, I inserted a pi. It's an easy mistake to make. Over 2r k-hat. The negative, I just distributed out front. Take out like terms, mu naught over 2r. That would be then I1 over pi minus I2 k-hat. And now it's just a matter of putting in the numbers. So that is 4 pi times 10 to the negative 7th newtons per amps squared over 2 times the radius, which is 0.030 meters, times I1, 8.0 amps, over pi minus I2, 2.0 amps. And when you throw all those numbers into a calculator, you get 11.4 microtesla, and that is out of the page. Whoops. So we talked about the Lorentz force law as it relates to a current carrying wire. So we discussed what is the force that a wire would experience carrying a current through some magnetic field. We didn't talk about what created the field or anything. But let's say we have two current carrying wires that are parallel. Will they exert a force on each other? Yeah, because wire number 2 creates a magnetic field. And this is the strength of that magnetic field. It's mu naught I2 over 2 pi A, where A is the distance away from the wire, which is also the distance between the two wires. So in other words, the magnetic field at this location where wire 1 is at is given by this expression. So what is the force on wire 1? Well, we go back to the Lorentz force law. The force on wire 1 is IL cross B, so that's I1L cross B2. And the direction of B2, again, right-hand rule, if you point your thumb in the direction of the current, fingers curl around the direction of the magnetic field. And so at this location, the field is perpendicular to the plane mapped out by the two wires. Well, the wires are both parallel, so the magnitude of F1 would be, ILB sine of phi, but phi is 90 degrees because magnetic field is perpendicular to L. So now I substitute in for B2 at that expression, and we commonly move the L to the other side. So we can say the force per unit length on wire 1 due to the current in wire 1 and the magnetic field produced by wire 2 is this expression, FB over L times mu naught I1 I2 over the quantity 2 pi A. If the parallel conductors are carrying currents in the same direction, they will attract each other. If they are carrying currents in the opposite directions, they will repel each other. So looking at this example, a long straight wire carries 20 amps. A 5 centimeter by 10 centimeter rectangular wire loop carries half an amp, 500 milliamps, and is 2 centimeters from the wire shown in the figure. Find the net magnetic force of the loop. Okay, there we are. So I've got this I1, and I've got I2 going in a clockwise fashion. So there's 2.0 centimeters here. And I'm going to call the length of this side A and the length of this side B. So I1 is 20 amps. I2 is 0.500 amps. A is 5 centimeters. B is 10 centimeters. Let's see, anything else we need to know? Okay, that's everything. So I can go back and label these sides 1, 2, 3, and 4 just for reference purposes. So the total force on this whole rectangular loop is going to be the F1 plus F2 plus F3 plus F4. And another note, just to remind you, when you're adding these vectors, because I put vector bars on everything, that incorporates the direction of each one of these forces. If I had been using magnitudes, I'd have to identify the positives and negatives, and that's what we're going to do right now. So let's look at sides 1 and 3 first, because I have some knowledge going into this about those two sides. So let's look at side 1 first. The force on side 1 is I2 L1 cross B1, where I'm calling B1 the magnetic field from the straight wire. What is the direction of this? Well, since the current is going clockwise, I point my first finger in the direction of the first vector, L1. That's kind of, I can't zoom out anymore. There we are. L1, and I point my second finger, the middle finger, in the direction of B1. Well, what is the direction of B1? Actually, maybe I'll just rotate the paper here. That'll be easier with the camera system I've got. So I point my thumb in the direction of the current, and my fingers curl in the direction of the magnetic field. So that means on this side of the wire, the magnetic field is into the page. On this side of the wire, the magnetic field is out of the page. But we are all of these things are below the wire. So B1 is into the page. So the current going through this leg of the wire is up. I put my middle finger in the direction of the magnetic field, which is downward, and so the force is to the left. So the force is, maybe I'll make this arrow a little bit. The force is to the left. What is the magnitude of the force? That's a little bit tougher to say because the distance away from this wire that's creating the field, the distance is changing. And the further I get away from that wire, the weaker the magnetic field gets, and so therefore the weaker the force gets. I'm going to have to integrate all of this. That sounds a little messy. However, if I look at side 3, and let me rotate this. So this current is this way, down on the page. It's up now because I rotated it. I point my middle finger in the direction of the field, which is into the page. My thumb points in the direction of the force. So F3, once I rotate the page again, is to the right. Now the magnitude is the same type situation. I'm getting farther and farther away from this wire, so the field is getting weaker and weaker, the force is getting smaller and smaller, but they start at the same distance away on each side and end up at the same distance away. So the magnitude of F1, the total force F1, is just equal to the negative F3. Therefore, F1 plus F3 is equal to 0. They sum out. They sum to 0. So all I have to worry about is the force on this leg and the force on that leg of the rectangular loop. So let's find what F2 is. So that's I2 L2 cross B1. And what's the direction there? Well, the current's flowing this way. The field is into the page. The force is up. Okay. That's F2. And the magnitude F2 is I2 L2 B1 sine of phi, but they're perpendicular. I is this direction. The magnetic field is into the page, so this is 1. F2 then is equal to I2 L2, which is the length of this wire, and that's B, times B1, which is mu naught I1 over 2 pi. I'm going to call this Y2. Y2 distance from wire. So the magnetic field of a straight piece of wire is mu naught I times 2 pi times the distance away from that wire, and the distance away this time is y2, and that is 2.0 centimeters here. So what is F4? Well, that's I2 again, L4 cross B1. So the current's going this way, the magnetic field is into the page, so the force then is down. In fact, I could make this a vector by saying this is j hat, and then I can say F2 is I2 L4 B1 sine of phi, which again is perpendicular. That should be 1, not 0. And that is negative j hat because it's downward. So F2 is equal to I2 L4, which is B again, times mu naught I1 over 2 pi again, but now Y4, because we're at a different distance away from that wire. The field drops as you get farther away. The field here is less than it is here, so the force on this part of the loop is less than the force on this part of the loop. So sum the two together. So that's just F2 plus F4. Oh gosh, I dropped. Excuse me. I dropped the wrong subscripts on here. So F2 I2b mu naught I1 over 2 pi Y2. And then add F4, which is going to be negative I2b mu naught I1 over 2 pi Y4. And these are both in the j hat direction. Positive j hat, negative j hat. So there are a lot of like terms here, which I can factor out. So mu naught b I1 I2 over 2 pi. I've got 1 over y2 minus 1 over y4 j hat. So it's 4 pi times 10 to the negative 7th Tesla per amps squared times b, which is 10 centimeters, or 0.100 meters, times I2, which is 20 amps, times I1 times I2, which is 0.500 amps, over 2 pi, times 1 over y2, which we know is 0.02 meters, minus 1 over, now what's the distance here? Well, it's 2 centimeters plus a, which is 5 centimeters. So it's 7 centimeters away. 2 plus 5, so it's 7 centimeters away from the source. And if, I'm going to have to squeeze it in at the bottom here. When you add all that together, you get 7.1 times 10 to the negative 6 newtons, positive j hat direction. Or you could put that, talk about that in terms of micronewtons. That's 7.1 micronewtons.